Welcome to Physics Made Easy channel. We are doing nuclei, and in nuclei we have done with binding energy curve and binding energy per nucleon recently, and now we shall be starting with the topic of packing fraction. Packing fraction is basically it is the mass defect per nucleon. Note this very word that it is the mass defect per nucleon. How? Mass defect. Mass defect is M minus A. M minus A divided by mass number A. So this is packing fraction. And we have also got a graph for packing fraction. So first of all, packing fraction is M minus A divided by A, where M is mass and A is nucleons, A is mass number, and M minus A measures mass excess. It is divided by A, which is mass number. Mass excess M. This is mass excess. This is basically a boxed expression. Mass excess is measured by M minus A, where A is mass number. Now unstable nuclei. First I will study the graph. All the nuclei with positive packing fraction, they are unstable. So nuclei, you can say this block of mass numbers up to 20, 16 in fact. For oxygen it is 0, and then it is negative, and here it is negative, and here it rises up again, becomes 0. So we have got these three fractions. This red colored nuclei, they are stable, they have got negative value of packing fraction. All these are stable. And they have negative value of packing fraction. And then this is larger than mass number 200. So these larger than mass number 200, they are the variables. They are the variables here. So it may be going out of screen. So they are larger than this. They are unstable. And I want to represent unstable by they are unstable, and in these cases it is the fission which takes place. So they are also unstable. They are lighter nuclei. From binding energy curve we have also concluded that lighter nuclei, they fuse together. So in this part of the curve fusion takes place. Fusion of lighter nuclei. And in this part, in this particular part, fission takes place. And we can say that this is fission. Fission of heavy nuclei. Fission of heavy nuclei. This part is fission of heavy nuclei. And all these nuclei, they are stable nuclei. All of them, they are stable nuclei. We use the word stable for it, and they are stable nuclei. These are stable nuclei. These are stable nuclei. Iron here again is the most stable nuclei. This is most stable. This nuclei is stable. Along x-axis we have taken mass number. Along y-axis we have taken packing fraction. Packing fraction is excess mass per unit mass number. It almost performs the same task as was performed by binding energy curve, but binding energy is more famous than this graph. But it is performing, or its significance is similar. We can explain the process of fission of heavy nuclei and fusion of lighter nuclei on the basis of even packing fraction. And now a broad review. Nuclei less than 16, they are nuclei less than mass number 16, they are unstable. Packing fraction for them is positive. And then we have got nuclei starting from mass number 16 up to this particular level. And nuclei here up to this level, up to 200, you can say the value is negative and the nuclei are stable. Above mass number 200, nuclei are unstable because their value has again become positive. So nuclei with positive value of packing fraction are unstable and nuclei with negative value of packing fraction are stable. Now packing fraction is directly related with the availability of nuclear energy and the stability of nuclei. And the next very important topic is nuclear forces. Nuclear forces are strongest forces on Earth, and they are the strongest force of attraction, which holds together the nucleons of tiny nuclei despite strong electrostatic repulsion between the protons. Now, nuclear forces, they are the strongest forces, strongest interacting forces, and they are short range, but due to their strength, they are able to overcome for a distance of up to, you can say, 10 Fermi, the long range electrostatic forces. Properties of nuclear forces. The first property of nuclear forces is nuclear force is the strongest interaction known in the nature. It holds nucleon together inside the nuclei despite strong electrostatic repulsion between the protons. Now the relative strength. If we put the value of gravitational forces at 1, then 10 raised to power 36 is the electrostatic forces shown by Fe. And 10 raised to power 38, they are nuclear forces shown by Fn. So nuclear forces are roughly 100 times more powerful than electrostatic forces. They are short range. Nuclear forces are short range. Their range is very short and they operate up to few Fermi, at the most 10 Fermi. At the most, what we can say, they operate at the most at the level of 10 Fermi. So their range is 10 Fermi. Now I will compare their range with angstroms. These are the nuclear forces. 10 Fermi. 10 Fermi means 10 raised to power. This means 10 into 10 raised to power minus 15 meters or 10 raised to power minus 4 meters. The range of electrostatic forces is 10 angstroms. So nuclear force, electrostatic forces, they have got range 10 raised to power 5 times more than the range of nuclear forces. Electrostatic forces, they are long range forces. If I put this, it will come out to be 9 raised to power minus 10 meter. So this is the case of nuclear forces. So this is 10 raised to power minus 14 and this is 10 raised to power minus 9. So if we compare, then electrostatic forces, they are about 10 raised to power 4 times longer in range as far as than nuclear forces. Now let us discuss next part, variation with distance. So this graph is almost same in all the three kinds of interaction. We have seen this in atomic forces, molecular forces, and then finally in nuclear forces. The range of nuclear forces, as I have already argued, is 10 Fermi. This is the range of nuclear forces. The range of nuclear forces is 10 Fermi. And this is, on this side we have drawn potential energy, positive potential energy, negative potential energy. Now as two particles are brought together, attractive forces, they keep on growing and they achieve their maxima at about a level of near about 40. Potential energy 40, if it to be slightly more than 40, you can say I'm taking approximately 40. Minus 40 MeV potential energy is the maximum attractive potential energy, and this takes place at about 0.8 Fermi. At about 0.8 Fermi, this takes place. Now we reduce these values further. We reduce these values and the force becomes less and less attractive. And at this particular point, it becomes 0. And now if we move the nucleons more closer than this point, then a very strong repulsive force develops. So this is the general shape of the graphs for nuclear forces, and I will like to remind the shape is almost similar with atomic forces, molecular forces, and then nuclear forces. The basic shape is similar in all these three forces. The basic shape is similar. Now, Variation of the graph I have explained. The graph of potential energy of a pair of nucleons as a function of separation r is shown. Potential energy is minimum at a distance of r naught for me. If r is less than r naught, potential energy increases rapidly with decreasing r. If it is greater, then gradually decreases to 0 with increasing value of r. It indicates attractive nuclear forces. So I have already explained you all the things in detail. Nuclear forces are maximum at r is equal to 0.8 for me. They are maximum here. It varies inversely, not as a square of distance, but depends upon some higher powers. Depends upon some higher powers. R raised to power 4, R raised to power 8. And then nuclear forces, they do have spin dependence. For R greater than 10 for me, nuclear forces, they become 0. For R greater than 10 for me, nuclear forces, they almost become 0. And now, we have again shown this graph. The negative potential energy signifies that the nuclear forces are attractive. Charge independent. Nuclear forces are charge independent, means the force between two neutrons, there will be nuclear force between two neutrons. Now neutron has got nil charge. Nuclear forces between two neutrons, and then in two protons, and then in neutron proton pair. It means there are nuclear forces between neutron neutron, neutron proton, and then proton proton pairs. So it means they are independent of charge. Nuclear forces, they have got spin dependence as well. Saturation effect. Nuclear forces, they obey saturation properties. Every nucleon interacts with its immediate neighbors only. It does not interact with all other nucleons of the nuclei. Spin dependent character. The nuclear forces between two nucleons have parallel spins is stronger than between the two nucleons having anti-parallel spins. If we have got nucleons of parallel spins, so in case of parallel spins, they are stronger. Nuclear forces, in case of nucleons, they have got parallel spins. In that case, they are stronger. Parallel spins means this, if spin of this is this and this is this, they are parallel spins. In this case, I have already written they are nuclear forces are stronger. Now, in case of anti-parallel spins, what is anti-parallel spin? If one is spin vector direction is upward, others is downward. These are anti-parallel spins. In this case, in case of anti-parallel spins, we have got comparatively weaker forces. It is comparatively, I haven't written comparatively, they are weaker. Now, Nuclear forces are exchange forces. It is due to exchange of constant particles known as muons, mesons or pions. Pions. Pions have got, and even neutral pion has got antiparticle. Non-central forces. Now, non-central forces are the forces in which the force between the two bodies or the two particles is along the line joining them. For example, we have got uh, central forces. What are the central forces? For example, we have got two masses. Force between them acts along the line joining these two particles. So gravitational force is central force, and then electrostatic force, two charge. Here I have taken two masses m1, m2. Here I have taken two charges q1 and q2. Forces between them are electrostatic forces, Fe. Electrostatic forces and gravitational forces, these two forces, they are central. Why? Because the force between them acts along the line joining the centers of the two bodies. But nuclear forces, they are non-central. They don't act along the line joining the two nucleons. For example, I may have one nucleon here and another nucleon here. Suppose this is neutron and this is proton. Forces may be like this. If this is their spin, because forces, they do depend on spin. Nuclear forces, the non-central part of the nuclear forces is due to spin dependence of the forces. And next is, they do not follow inverse square law. Nucleons themselves are built of subunits called quarks. Thus, the nuclear forces is a secondary or spillover effect of a strong force that binds the quarks together to form neutron and protons. Quark forces caused by exchange of massless glucons. So, we have proceeded further. Neutrons and protons, they are not the fundamental particles, they are made up of some subunits. Those subunits are bound by a force which is even greater than the nuclear force. And the particle exchange in those forces is called glucon. With these words, I finish this session of the lecture. And before closing this lecture, I will request all of you to comment if you don't like the video and to share if you like it. Thank you very much.